All right, welcome to The Explainer. Today, we are taking on a highly tactical culinary mission, Operation Alfredo. Now, if you've ever tried to bake a traditional cream sauce and just ended up with this disastrous broken mess in your pan, well, you know exactly what we're up against here. Our objective today is pretty simple, but absolutely crucial. We're going to engineer a structurally sound chicken Alfredo casserole from the ground up. The end goal? A cohesive, perfectly sliceable matrix.
Okay, let's dive into this. Here are the 6 operational protocols we'll execute today to build this high-density macronutrient payload. We'll start with the Alfredo casserole problem, move into Protocol Alpha for a stabilized sauce, then Protocol Beta for component engineering. After that, it's Protocol Gamma, covering starch limits, then assembly and thermal fusion, and finally, we'll wrap up with the authenticity debate.
Right into Part 1, the Alfredo casserole problem, or surviving the thermal environment.
So, to really understand the primary threat facing our mission here, we have to ask a crucial question. What actually happens when you take an authentic, traditional Alfredo sauce and subject it to prolonged, intense oven heat? Like, why does taking a stovetop classic and just, throwing it in a baking dish almost always end in catastrophic failure?
Well, here's the harsh reality. It violently separates into a literal pool of grease. See, authentic Alfredo is a highly fragile emulsion. When you trap it in a 375-degree thermal environment, that emulsion just completely breaks down. The milk fats and the cheese lipids actually divorce from the liquids. So what are you left with? Floating oil and mushy, unappetizing pasta. Without chemical intervention, your casserole is doomed before it even enters the oven.
So, what does this all mean for us? It means our solution requires us to abandon traditional Alfredo entirely. Yeah, you heard me. Instead, we have to engineer a starch-bound dairy sauce. Now, technically speaking, this is a Mornay and bechamel hybrid. By utilizing a chemical barrier of flour, we can physically prevent those milk fats and cheese lipids from separating when things get hot. This hybrid sauce, it's the structural foundation for the whole shebang.
Moving right along to Phase 2, Protocol Alpha, stabilized sauce. Let's build that chemical barrier.
Now, what's really interesting about this slide is the exact chemical sequencing of building our fat and starch barrier. Step 1 is the roux. In a large Dutch oven, you melt a 1/4 cup of butter, toss in some minced garlic for just 30 seconds, and whisk in a 1/4 cup of flour, cooking it for exactly 2 minutes. That coats the starches in fat and totally eliminates that raw flour taste. Then, Step 2, hydration. We slowly whisk in whole milk and heavy cream, bringing it up to a simmer so the starch granules actually swell and thicken the liquid. Finally, Step 3 is the cheese matrix. You absolutely must do this off the heat. We blend in freshly grated Parmesan for flavor, and this is key, mozzarella for binding elasticity, and then season it aggressively.
Okay, on to Part 3, Protocol Beta, component engineering. Let's get our proteins and vegetables prepped.
To build our payload, we're focusing on 2 main additions, the chicken and the vegetables. For the chicken, we dice it into uniform 1-inch cubes and sear them in olive oil for about 4 to 5 minutes. The goal here is solely to achieve Maillard browning on the exterior for flavor. You intentionally want to leave the core completely uncooked. Seriously, if you fully cook it now, it's going to totally dehydrate in the oven. As for the veg, broccoli florets are structurally optimal to pair with our pasta, but they require incredibly precise temperature management.
And that precise management comes down to a single number. 2 minutes. Raw broccoli won't cook enough in the casserole, but fully cooked stovetop broccoli? That turns into absolute mush in the oven. No one wants that. You must blanch the florets in boiling water for exactly 2 minutes, and then immediately shock them in a bowl of ice-cold water. This rigidly halts the cellular breakdown, preserving their structural integrity for that final bake.
Which brings us to Section 4, Protocol Gamma starch limits. Let's talk carbohydrate hydration parameters.
Believe it or not, the geometry of your carbohydrate matters immensely here. We specify penne rigate. That tubular shape with its internal cavity, combined with those external ridges, completely maximizes surface area. It's like a giant puzzle piece. This specific structural geometry is exactly what's required for the pasta to physically anchor and hold on to our heavy, stabilized dairy sauce. A smooth or flat pasta just is not going to perform the same way in this matrix.
And here is another critical number for you, 3 to 4. This represents the exact minutes you must pull the pasta from the boiling water before the package's recommended al dente time. You heard that right. The pasta needs to be extremely undercooked and kind of chalky in the center. Why? Because as it bakes in the thermal chamber, it's going to absorb the excess moisture from our dairy sauce.
If you cook it fully on the stove, it's going to become incredibly gummy and bloated in the oven. Pulling it 3 to 4 minutes early guarantees perfect starch gelatinization.
All right, part 5, assembly and thermal fusion. Time to bring the payload together. So in a massive mixing bowl, you gently fold the par-cooked penne, the seared chicken, the blanched broccoli, and that stabilized Alfredo sauce together, making sure every single component is beautifully coated. Then, as the source material dictates, transfer the payload into a greased 9 by 13-inch baking dish. We are finally moving our assembled matrix into the vessel where it will undergo a 375-degree Fahrenheit thermal fusion.
But wait, before it enters the oven, we have to deploy the lipid shield. You just blanket the top entirely with 1.5 cups of shredded mozzarella cheese. Now this isn't just for taste or aesthetics, though obviously it looks amazing. This is a highly functional shield. It physically prevents the surface pasta from dehydrating and turning into hard, inedible shards during the 20 to 25-minute bake. It literally locks in the moisture of our matrix until the edges bubble and the shield shows off those perfect golden brown spots.
And finally, Section 6, the authenticity debate, the red team counter-analysis.
To evaluate the cultural implications of what we've just built, we really have to look at the divide in the culinary world. And this brilliantly illustrates it. On one side, we have authentic Italian Alfredo, a dish with pure Roman origins. On the other side, we have our engineered creation, the American Casserole, a total pillar of Midwestern comfort food. Let's look at the data impartially. Breaking down the data here, culinary purists are technically absolutely right. Calling our casserole Alfredo is kind of a misnomer. Authentic Italian Alfredo uses only pasta water and butter as a liquid base, whereas our casserole uses milk and heavy cream. Authentic Alfredo uses 0 thickeners. We use a flour roux. Authentic Alfredo has no add-ins, but we've packed ours with chicken and broccoli. And thermodynamically, authentic Alfredo is delicate and requires immediate consumption. Our casserole is engineered to withstand heavy oven heat. So technically speaking, we've engineered a French-American chicken and vegetable gratin driven by caloric density and large-scale feeding. Definitely not an Italian Alfredo.
Which leaves us with this final, provocative thought. When you step into your kitchen, what are you actually optimizing for? Is the true magic of food found in adhering strictly to its authentic cultural origins, preserving the delicate traditions of the past? Or is the magic found in the scientific engineering we use to maximize its thermodynamic comfort, yielding a dish that can feed a huge crowd and actually survive a 375-degree oven? Whichever side you lean toward, you now have the exact protocols to engineer the perfect casserole payload. Thanks for joining me on this explainer, and I really hope you're inspired to experiment with these food science concepts in your own kitchen.